My field was function theory and Vekwa theory in my diploma thesis, and then I came home, I made my Kandidatske, and then I was looking to another field, my own field in research, and it was the time when people were speaking about Clifford analysis or hypercomplex analysis, which was founded in the 13th already of the last century. And since I was a believer that one can do everything, almost everything, also for higher dimensions, I started to work, and luckily I found something. And this has to do with hypercomplex Appel polynomials, and you see here something more written, Wigner numbers and quantum mechanics, and also a little bit geometry if you want. Pascal trapezoid has a touch of geometry, because it is a structure that we could detect. And I tell you, it's rather new results. You will see, and I start. It's better to start. Together with my colleague Irene Falcao and also two other former PhD students, I'm working still. And I'm very happy that I can also speak about these things here in Armenia. So what is going on? I would like to speak first to come into the field about Wigner matrices and Wigner numbers in quantum mechanics. And you see, this is not only considering a function, but it has to do with numbers and even number theoretic results we found. But to understand this, the connection with the hypercomplex analysis, in the second part, will speak about this paravector valued monogenic functions of a paravector in Rn. These are generalized holomorphic functions. In fact, then, as a special case, we consider polynomis, Appel polynomis, because Appel polynomis have properties like power function. And this was also a question open if it exists a meaningful type of polynomials which can be used in several fields. And here the third part will also mention different presentation of these polynomials, and from the different presentations with different coefficients in the polynomials comes what we could now find and connect with Wigner numbers from quantum mechanics. So very short, what I would like to say, is very short hint of a paper where one can read very well the historical background also of Wigner's matrices, which he introduced already in the 30s of the last year to deal with angular momentum and rotations and everything stuff. So, and here, as in the middle of the harmonic analysis, we have spherical harmonics, and then we have the problem of rotation, and for the description of the rotation of this matrix is important. In quantum mechanics, Wigner introduced matrices. But matrices, you know, this is a set of numbers in a matrix form, and the values of these numbers can be interesting. And this, to mention the steps for quantum mechanics, and that when we are speaking about harmonic analysis, it is not only a field in physics, but also the chemistry is interested for the description of rotation of molecules, for example. And as I told you, the first edition was in 1931 in German, and then Wigner came to the States, and he wrote this book, and in 1944 it was already translated, and in 1959 a new edition appears. And this was just when really quantum mechanics opened a new workspace for spherical harmonics. And what is important, and important also to understand why what we are doing with the numbers has to do with combinatorial problems, with recurrence relations. It was this paper from '98, so it's not so long time ago, where the rotation matrices and on the basis of weakness results in group theory were outlined, and the next paper dealing with this for simplifying and find an alternative approach to weakness matrices. We have this paper from 2013, and then these two papers were in 6 years ago, were introduced Wigner numbers as characterizing these matrices, and two Hungarian, they noticed the relationship to combinatorial problems. It's natural. You know, Hungarian mathematics is to big time, to great time, it's combinatorics, and so it was not strange that in this paper we found something surprising, because if we look to the introduction of the numbers, then it has to do with this matrix representation and for different spin, for the rotation moments, and then in 2019 only were introduced these Wigner numbers in this form by Allen. And what happens? We have this paper from 13, we have this both papers, and in the middle, 1 year before the Wigner numbers appeared, we had already found some combinatorial identities, and which are based on hypercomplex or multidimensional polynomial sequences. These are my colleagues, and we published this in the Journal of Integer Sequences, a very interesting paper, maybe you know, journal. And to come now to our numbers, and later on I will show you the connection with Wigner numbers. I shortly explain something about generalized holomorphic functions. They are based on generators of Clifford algebra, and this is a generalization of the complex algebra or quaternion algebra. And you have for the generators, which are, form an orthonormal basis in the Euclidean vector space Rn, you have this condition, the multiplication rules is behind. Then you have this, because the dimension is rising up, you need not only this, but products of them. And because these are non-commutative generators, we have a growing up of products which form the basis for this function which we would like to consider. So, and if you identify the Rn plus 1 as embedded in the Clifford algebra with this basis, then you find this type of paravectors, so a scalar part and a vectorial part, which are spanning An as subset of the Clifford algebra. And we have, and this is the connection with the complex case, we have a conjugate element, we have, which is defined in this way, we have a norm, we can also consider such problems. And what is most important, we have operators which are in the type of the Wirtinger operator describe the set of the functions which are in the kernel of this operator. But we have also, this was also done in 1999 in a work with my colleague from Germany, Klaus Görlebeck. We could also justify to consider the conjugated differential operator as the hypercomplex differential operator. So we have also the possibility to consider the differentiation of this class of monogenic function or generalized holomorphic. But we need to consider from the left or from the right the action of the operator on the function. So, but important is here that the function can be written with the basis of the Clifford algebra in this form. The coefficients are real valued. And yeah, I can even not well remember, but it was 20 years ago, we were eager to find a type of power-like, as I told you, monogenic functions. This was also an open problem because the differential operator has to come in. We were looking for polynomials built by x and x bar, and we had to define the coefficients, the corresponding, to get here a polynomial which is fulfilling just this Appel polynomial condition. I will show you. Interesting that the structure of this coefficients, it's very clear. It is a partition of the unity, in fact, the set of these coefficients, and they are built by these elements. And then we have here the idea, because we have different representation of these polynomials. To combine which the set of coefficients, this is a set responsible for building the polynomial of degree k, and this is one only coefficient if we use another form. So the idea, and it's not so easy, you see k appears only once, and all the other real coefficients have to be used, but we could already in the time prove that we have a matrix, the structure you see, it's very clear, which combines the set of this T kappa n in this form with the right side of the equations. You see, we had to take, because these are only from 0 up to index k minus 1, k, but we have k plus 1 t coefficients, you see, and to get the right way, we had to use the alternated sum of these coefficients, and because they are forming these coefficients ck. But it is not so clear how to find the matrix which combines the vector of this coefficients responsible for several degrees polynomials with the set of the vector. I show you again. This is a set which is not directly visible combined with this, but luckily we get that this is possible, and then we were looking for the inverse relation, and this inverse relation gives matrices which can only recursively defined. And I did not tell attention that also the theory of weakness numbers had to do for big numbers with recursive rules. Here it appears in this way. But when we tried now to understand better the composition of the matrix nk and the conjugated, we found that the coefficient 1, or set of all up to k, is formed by a special, very special, from the combinatorical point of view, very easy. No? It looks nice with binomial coefficients here, composed in such a way. And since we were, after this, also looking to generating functions of all the sets, to recurrence rules for the sets, we came also very quick to the use of the hypergeometric functions and Jacobi polynomials. You have here different representation, you see, through the hypergeometric function and through the Jacobi polynomials. So it's poor and old analysis, but interesting. If you find these connections, you feel it exciting, and you have to go further. And since, this is already too much, what we proved, first of all, the easiest form when I is 0, we have the Pascal triangle as composition of these numbers. And if we have the case I equal to 1, then we get a Catalan triangle. We knew that the Catalan numbers appear there, they are connected because the central binomial coefficient appears there. And then we saw that in 2017 only such a Catalan triangle was studied. It came together year by year. And in this case, we have, you see, this is like for the binomial coefficients, the same rule, the recurrence rule. From an element of the k raw, you get, in the same rule like it would be binomial coefficients, you get an element from the next. But we have, in this case, boundary conditions. If you use all these indices, we have to work with boundary conditions for this triangle, corresponding triangle, and also initial values. So, and there are two parts. This is this relation, and we have also the appearance of a difference of elements, but not from the same raw. You see here a difference with one element from the k plus 1 raw, and then you get this new element. And other initial and boundary conditions. And it depends. Both combination allow to consider different triangles, because in one triangle we let run G, and in the other triangle we let run I. Yeah. So, and then this ends up, here are appearing, depending from, and here I have only one part, it's only an example where G is running and I is fixed. G 0, 1, 2, 3, and it appears that in the first moment we have triangle, and then the upper part becomes 0, the elements, because of this ordering. And so we have here a triangle, but then following are Pascal trapezoids. That's here the interesting moment. And of course, we studied a lot of properties. These are only examples. We have symmetry in special trapezoids. We have also the, you see here the connection with the Catalan numbers. And it's, from the combinatorial point of view, interesting. I never was thinking that such things would cause my interest, but it's nice. You know, the basis of all mathematics is geometry and numbers at the end. And to come back now to the connection of the elements of this Pascal trapezoids with the weakness numbers, I have here the formula which appears in the paper of Allen in 2013, and 13, yeah. And this is the paper of these two Hungarian. They noticed that this writing can be simplified. It's not running from max and min, but it can be written in such a way. The same numbers. You see, for the values of G. And if you compare these numbers with this form, then you see which substitution of the coefficients are necessary. And then the paper of this Hungarian, they extended to not to have only 2 in the matrix here, you see. They extended to L Wigner numbers. And then you have immediately the other substitution by this value, so we can, in this way, Wigner numbers consider as entries of Pascal trapezoids. It looks rather elementary, but also the authors of this paper noticed that, in fact, we have here an interesting combination of two fields, combinatorics and hypercomplex. And this is the power of the hypercomplex case, that you have possibility to generalize things which normally appear only as numbers in complex or real analysis. And we had already before, we had introduced Vietoris numbers. And I noticed that I jumped here. I want to show you where it comes in our approach. This I did not show you, the coefficients explicit. And here the combination or the expression, also a second expression, and where is what I want to show you? Here. Because there is still another presentation of the Appel polynomials. If you are using several hypercomplex variables, they are built in such a way that you have a real vector, like in the case of several complex variables. In the complex variable, you join to this real vector a second vector by the imaginary unit. And here you see the duality if you, to the real vector from Rn variables, join with the R plus 1, with the variable x naught, the special variable, a vector of the generators, then you see the similarity, of course. Yeah? We studied also the presentation of this Appel polynomials only by the hypercomplex variables and the generators, and this is a structure. And therefore we need only for each polynomial one coefficient. You see? This is amazingly. And for example, written explicitly, the first Appel polynomial of degree 1, we see here we have the Tn, the sum gives 1, you see, and we have this presentation, and here's the Cn, and we can also, if we use the properties of the Appel polynomial, that in the point 0, if we are evaluating the polynomial in point 0, that they give you the value of the Ck coefficient only expressed in this general structure by the generators. So, and Ck is real, yeah, but this is an expression by hypercomplex generators. Also, we use it in several other connections to take use of this. So, and now I jump again to this. We have here still the representation of the matrix and the Pascal-like recurrences I showed you, the trapezoids. And this, the other paper did not notice the ordered structures. They explain the appearance of zeros in the upper part as properties, special properties when the index are combined in such a way. We have here, and this was very exciting, and we've studied also trapezoids, Pascal trapezoids, also another connection, for example, in parallel epipades where such triangles are important, that you have now the possibility with hypercomplex variables to see behind the set of numbers only described by formulas. You see now a geometric structure. And it's very useful for practical applications. So, yeah, Wigner numbers can be considered as entries of Pascal trapezoids I on the end. Thank you very much for your attention.